The objective of this video is to derive the space vector representation for forces in a p plus or minus 1 pole pair bearingless motor. We want to be able to write our force expression like this, that is, the forces produced on our shaft, which I've denoted Fm, as being equal to a complex quantity Kf times our suspension current space vector. And in the rest of this video, I'm simply going to refer to this as F. But if you'll recall, we previously said that our bearingless motor control model is going to be an expression that looks like this. So our bearingless motor control law, our linearized control law, is going to be this expression, and that's what we're ultimately working to build up to. But in today's video, we're going to instead focus on this portion of that. That's the first set of terms here. And we're going to denote that as this vector F. So if you recall from our last video, where we derived the forces that act on our shaft in this matrix form over here. And so simply put, the purpose of this video is to take this matrix form and come up with this force expression. So let's review this expression here. We have this quantity sigma s, which we had written in terms of our magnetic and electric loading. And actually, as you see it right now, we have our electric loading, but then we have this quantity Bm hat, which was not precisely our magnetic loading. In fact, it came from the sum of our magnetic loading and our armature reaction. So here's our magnetic loading. This appears in the air gap of the machine, as well as an additional radial field that's caused by our torque winding, and we denote that as Bw. So we sum these fields together because they both have the same number of pole pairs, and that resulted in this field expression here, which we use in deriving our force expressions. So this field expression has a peak value and then a location in the air gap. So that's this term right here. Next, we have the volume of our rotor, and then we have the number of pole pairs of our suspension field times our air gap length, and again we have the radius of our machine. Coming back to this quantity sigma s, I want to work out how this looks in terms of our current space vector. So we defined our suspension current space vector to have the following form. That is, it has a magnitude, and it has an angle, which we were referring to as alpha s. And we related this to the peak of our linear current density on the surface of our stator, on the surface of an equivalent slotless stator, as follows. And if you recall, this quantity right here refers to the per phase circumferential current density due to the suspension winding. And so we had defined this function that could be used to calculate the circumferential current density of each phase of the winding. And the reason I have this S here is to keep track of the fact that this is occurring for the suspension winding. The pH indicates that this is a phase quantity, and so this is related to the winding functions of our machine. We had noted this in our review video. And then finally, let's review what our current space vector means. We can relate it to the three-phase currents in our machine with the following relationship. So we have three-phase currents that have a magnitude and an angle. And that relates to the magnitude of our suspension current space vector by being 3/2 the magnitude of each of our phase currents. And the angle of our space vector is at this same angle. Alright, we're now ready to begin the core of this material. We can rewrite our force expression as follows. We're going to plug in this quantity into here, and then we're going to use this relationship to get this in terms of our current space vector. And the thought process here is that in our previous video, we were studying the bearingless motor from a machine design perspective. That is, we wanted to be able to understand if we have certain fields in the air gap of our machine, how much force we're creating and in what direction. However, in this video, we're trying to shift our focus to study the bearingless motor from a control perspective. That is, we know that we want to create a force in a certain direction. What currents do we need to flow to make that happen? And so to that spirit, we're going to shift this expression from being in terms of the ratings of our machine, that is the magnetic and electric ratings, to being in terms of a current space vector. And so we've written this expression out now in terms of this portion right here, and then the magnitude of our current space vector to the right. And this portion on the left that I've underlined in red, we are defining this as the magnitude of kf. So this is kf hat, that's the magnitude of this quantity right here. And so we are simply defining that. You'll see why as we move forward in the video why that is the magnitude of kf. And so the first thing that we can note about kf hat is that it is actually a function of our torque current space vector. And we can see that because of this quantity bm hat. In fact, if we go back to our review side over here, this right here is the magnetic loading of our motor design. And this quantity right here is the armature reaction field, which is produced by our torque current space vector. Our torque current space vector changes this field, which in turn changes this, and changes this. For a lot of motors, this can be negligible. This is especially true of surface-mounted permanent magnet machines where you have thick magnets. You actually don't create a lot of field with your torque winding. So oftentimes we'll just assume that BW is 0, which means that BM hat is simply equal to B delta hat. That is, it's simply our magnetic loading. The second thing I want to point out is that we can do a little work on this expression to have kf hat be purely in terms of machine design parameters. If we assume that armature reaction is 0, this term becomes B delta hat. Well, the volume of our rotor, the radius of our rotor, all that is clearly a machine design parameter. Same with the air gap length and the number of pole pairs. But what's a little bit confusing to talk about is what is this quantity here in terms of our machine design parameters. So let's quickly come up with an expression for that. And we're going to do that by making use of our observations over here. That is, we're going to relate this to our electric loading and the current rating of our suspension winding. And so to write this expression right here, I'm simply solving this expression, and then I'm noting that we're evaluating the magnitude of our current space vector at the rated current of our machine. And then we can use this relation over here to express the magnitude of our current space vector in terms of the rated terminal current of our machine as a peak value, which we can then relate back to the RMS quantity. So normally when you have an electric motor, you talk about the current rating of the motor in terms of the RMS current, which is what we're doing here. And we can get, if we plug this in, we get a final expression like this. And now, if we put this expression in up here, we can express our force constant in terms of purely the design parameters of our electric machine. So that is, we've got a rated electric loading for our machine, we've got a radius, and we've got the terminal current of our machine. And then, as we talked about earlier, all these parameters up here we already know for our machine. The final thing I want to point out about this force coefficient is that we typically find the magnitude of it either experimentally or via finite element analysis. It's highly dependent on the saturation state of your steel, so while you can use this expression to calculate it, it will oftentimes be quite inaccurate. This expression is useful for capturing trends in the design space. You can see how your force expression may scale if you increase your electric loading of your machine, or if you change your air gap length or increase your number of pole pairs, but it's not going to be useful for getting a very accurate expression for control purposes. So oftentimes you're going to want to do either an experiment to measure it, or you're going to want to use finite element analysis. So what we've done is we have now found the magnitude of this expression. We're going to start to talk about the angle of this quantity as well. And then we're going to tie it all together to show how it can be related to the current space vector to create this force vector. And we're going to do this by considering P+1 motors separately from P-1 motors. So I'm now going to write out our force expression for the P+1 motor. I'm going to do it by referring to this matrix up here and writing this in a complex vector notation. We'll write out our force vector is equal to an x component plus an imaginary y component. And so again, referring to this equation, this whole term is kf hat, and you see that down here as kf hat. This term, magnitude of our current space vector, is again down here the magnitude of our current space vector. And similarly, I brought down the cosine and sine terms and attached the appropriate real or imaginary unit vector to them. And so if we use Euler's law, we can express this as an exponential. What I'm going to do now is plug in for phi si the angle of our current space vector. So if you recall how we set this up in our previous video, we defined alpha s, which is the angle of our current space vector, to be equal to theta, which is the location of our direct axis in electric radians, is the location of our north pole in electric radians, plus this quantity phi si. And so we can solve this expression for phi si to insert alpha back into our equation. So we're just undoing some of the simplifications we did in our previous video where we were concerned about the force sizing. And if we do this, we can get the following expression. And we've now reached our destination. We've achieved what we set out to achieve. So we wanted to write our force as this expression up here, a complex phasor times our current space vector. And you can see that we have managed to do that. We have a complex phasor times our current space vector. And so we can summarize our results like this. We've got our desired force expression in terms of this complex phasor, which rotates with the rotor's angle and has this phase offset phi m, which was due to our armature reaction field. And perhaps more interesting, or more to the point for controls, is that we can use this expression to solve for our current space vector. That is, if we know that we need to create this force vector, we can divide that force vector by our complex quantity, by our complex current gain, and we get out the current space vector that we need. And so the remark on this is that this motivates the idea of field-oriented control of bearingless motors. And so you can see that the angle of your current space vector is going to be the angle of your desired force vector plus the rotor's direct axis angle plus the quantity phi m, which is due to your armature reaction. And finally, we're in a position to summarize the coupling that we get between the suspension and torque production. So our armature reaction field modifies Bm hat, which changes the magnitude of our force per current gain. And the location of our armature field modifies the angle of Kf, which impacts the angle calculations right here, or right here. So all this was for the P+1 motor case. We'll now do the same thing, but for the P-1 case. So that is, we'll have a negative sign. And so you can see I've written out the equation, which we had up here, which was from this matrix. I've now written this out following the P-1 case, which puts a negative in front of the sign. And here we see that negative. So we'll work with this. Until we get in this form here, what you see from this is that we essentially end up with the conjugate of what we had previously. So in this expression up here, note that the angle of our Kf goes by a negative theta plus Vm. And of course, the angle of our current space vector goes by alpha s. Now, in our new expression, the angles are reversed. So here, the angle of this term is positive, and the angle of this term is negative. And so we can observe that what we get is our force is equal to the conjugate of that expression. And it's a little bit more useful to write this as the conjugate of the force when we're talking about our control. And so we finally end up with this expression here, which is the conjugate of our force. That is, if we write F as being Fx minus Fy minus Jfy, then we can express the right-hand side as the same as we previously had. That is kf bar is space vector. And the reason that we would prefer to do it this way is so that we can solve for is in a more conducive manner. And so just as we noted up here what the angle of alpha s is, we can do a similar calculation for the p-1 case. And we get the same expression, except for that we have a star, or we have the conjugate of our force vector. And the final thing I want to point out to you is that not only does your angle change when you're calculating your p-1 currents, but your magnitude changes as well. Because remember, this term right here, if we go back to this expression, has a plus or minus of 1 by r. And we can see from that expression that this is always going to be smaller in the p-1 motor case. So that concludes this video. In this video, we have derived the space vector representation for forces acting on the shaft of a p+or-1 pole pair bearingless motor. And we did this by first reviewing the results of our force video and then writing it in a manner that's more conducive for control purposes, that is, separating out the physical quantities of our machine from the current space vector that we're applying to our phase winding. And we came up with this expression right here, which gives you a very easy way to calculate the required terminal currents from a force that you desire to create. That is, you desire to create this force vector F, and then you can quickly calculate what your terminal currents need to be in order to make that force happen. So we did this both for the p+1 motor case and then for the p-1 motor case, and we got the same expressions except for we have a conjugate in the p-1 motor case for our force vector.